So the most important module of the platform is the risk assessment module. The risk assessment module estimates the risks of an asset given the possible material degradation due to climatic phenomena, but also can make predictions even for the situation of the asset in the future if no actions are taken, but also if we take any adaptation options such as strengthening the structure, changing some of its elements, etc. At pilot 3, first of all, the platform displays a map, and here we are in Italy, and there is a drop-down menu at the right, at the left of the platform, and where you can select, the user can select the list from the list of assets. Here we have only the Catinara Hospital, so I click on Catinara Hospital, the map zooms on the location of the location of the asset, and then if I press on the assets, the graph of the asset, which has been created by a BIM model, you can see a window which slides from the right, and we have first the general information such as the year of construction, the asset owner, and the description of the asset. This was also made by Vasilis previously, that the asset was designed in 1969 and constructed by 1947, etc. Then we have some information regarding the structural model characteristics. So the main material of the structure is ordinary Portland cement. The adaptation options, as it was, and I will show what I mean later on, but based on the material degradation results, there was not necessary, because we found that the concrete has not been affected as for today by climate change. And I think, Mr. Kalidromitis, you mentioned that there was also some test a few years ago, some samples taken from the hospital, and based on that samples also there was not found any degradation in the properties of the materials used in the construction. And for the fragility assessment, we call it cause specific because we know that the main hazard is the wind speed. If we had the opportunity to present the pilot one, then we had followed, the University of Birmingham followed another approach, a cause agnostic, but let's keep that. We have considered the effect of wind speed on the structure's behavior. And of course, the user may download the BIM model if he or she likes. The next module is the material degradation. So I think that it is well known that the climate effects, such as temperature, and also in collaboration with air quality, carbon dioxide emissions, etc., have an effect on structures, and they make the structural materials to deteriorate, so structures may be vulnerable and lose part of their strength. For these structures, as we said, it is a concrete and it is close to an urban area. So based on literature, the most important deterioration mechanism is the carbonation-induced concrete corrosion. For this reason, we got some models, empirical models provided by current literature, and we applied those, and we made some calculations in order to predict if there is an issue with corrosion of the steel rebars of the structure. But if you go to the literature, you will see that these models use as inputs the climatological variables. So we got climatological data from our partner Finnish Meteorological Institute, FMI, and for different SSP scenarios. I think that Marco, in the previous session, talked a little bit about the different SSP models which are related to the greenhouse gas emissions. And in this case, we consider these 4 scenarios. So if the user selects click on this, then we end up with a curve, a graph, which shows the carbonation depth in centimeters. So what is the carbonation depth? Is the depth to which the carbon dioxide has penetrated, and it might has led to corrosion of the steel rebars. In this graph, you see the carbonation depth, and also we had to make some assumptions because we didn't have the precise data for the construction. In our models, we need a lot of parameters, but a very important parameter is the water to cement ratio, which was assumed to be 0.5 in our case, and a concrete cover depth, which after talking with experts, and especially Mr. Kalidromitis, who is an expert in construction engineering, we thought that an assumption of 3 centimeters is valid for this type of building. Based on that, you can see in the graph that we have the cover depth as a dot line, which is our limit. And if we take one by one the scenarios until the end of 21st century, by year 2099, since we had data available, the prediction models provided available data since that year, we can see that the carbonation depth, even in the worst case scenario, will be lower than 3 centimeters. So our structure seems to be not to be affected by corrosion of rebars due to carbonation. And some extra functionalities of the graph, the graph is interactive. You can play with that. You can eliminate the graphs that you don't like. For instance, let's say that you are interested only in the worst case scenario. So you can keep on the worst case. You can reveal more in order to have, comparisons. And also we have integrated the diameter loss. Of course, since the carbon dioxides have not penetrated up to the level of the steel rebars, we have zero loss, and we are going to have zero loss by the end of century. And the remaining diameter, let's say that we have a typical rebar of 20 millimeters in a column or a beam of the structure, it's going to remain the same in all scenarios considered. So this is the material degradation model, which is a first step. In other words, since we are interested in climate adaptation, this provides us a picture of what is the current situation or the future situation given the change we made, and if no actions are undertaken. For this, we are in a good side. I mean, we expect to have no influence. In other structures, for instance, in the pilot one of the bridge, we found that by the end of century, if no actions are taken, then corrosion issues are going to be present. Now we move to the next module, which is the LCA-LCC. This is life cycle assessment and life cycle cost. For this, the University of Stuttgart was the responsible partner performing the life cycle assessment and life cycle costing. What we are saying about life cycle assessment, over the course of life of a building, what will be the impact of construction, maintenance, or in case you are taking other measures. And the life cycle costing is, the impact is, for life cycle assessments is the environmental mainly related impact, but the life cycle costing is related to monetary impacts. For the case of the hospital, during in the life cycle assessments, five different options of using different concrete types with different characteristics were assumed, and they were provided by our project partner BIBM, who are experts in concrete industry. So based on that, you can see that you can use different strengths of concretes with different impacts in carbon footprint, etc. You can end up with graphs, and in this case, in the platform, we were provided with the global warming potential in kilograms of carbon dioxide equivalent for various replacements, for various levels of percentage of replacement of the structure. So in this graph, you can see that if we replace a part or even the whole structure with each type of concrete, we end up with the GWP. And again, you can play with the graph. You can keep the one that you are more interested. And also, as you can see, the first two curves are identical. So in this case, although we have 5 different options, we end up with 4 curves. Also, we have, I think, oh, yeah, we have also other scenarios. If let's say that we replace only the pillars of the structure, and for different percentages, we end up with the corresponding environmental impact, only the traverses and the planar sections, etc. So overall, this is very good for decision making. I mean, you may have, or if you are the asset owner and would like to do some replaces, or you are required to do some replaces, let's say in case you had corrosion, or you need to strengthen the construction, you can decide upon between the different options. And this is an important outcome of the platform. You can have all the information together, and it's easier to make a decision or support your decision to an audience. The next module is the social impact. For the social impact, the corresponding partner was the University of Groningen. They use some microsimulations analysis in order to estimate how the state of the asset, the state of the hospital, if it is open, it is fully open, or partially open or closed, affects the well-being of citizens. And for the well-being, they consider 2 main components: the happiness and the life satisfaction. And as you can see, in most cases, when the asset is open, it has a positive impact on life, on well-being of the citizen. But when it is closed or partially open, then the impact is negative. Furthermore, they perform some extra analysis, and for different, social categories like the males, the people, the income, etc., in order, to assess if these parameters corresponds to the life satisfaction related with the function of hospital. And now we have also another function of the platform, which is the scenario builder, because this is very important, because based on that you can estimate the probability of failure or of being in a damaged state. For the case of the hospital, as we said, we have only one scenario, the assist case, because we didn't use any adaptation options. So for this reason, the user, what simply has to do is first to start with a scenario of climate predictions of greenhouse gas emission. Let's pick the worst one, and then you can go to the year of interest. Of course, since we have data, you can go to previous years, but I think that for now, more important is to go to the future. Let's say that we go to 2050, 25 years from today. And then we select one of the climatological models. The climatological models, what is the difference between the SSP and the climatological models is that there are some models that can predict the wind speeds of future conditions. And Marco talked about that in the previous session. So all the models which give us the probabilities of extreme wind speed values for future periods and past periods were integrated. I will pick randomly one, and what you get from that is first the fragility curves. The fragility curves are provide the probability of being in a damaged state, and we consider 3 damaged states: moderate, severe damage state, and critical damage state. The critical damage state is actually when the corresponding safety factors leads to collapse. And for various values of wind speed, you can have a probability of being in a state. Of course, for a specific wind speed value, the probability of being in a moderate state is higher than the severe and the critical damage state. And this is the first leg of risk assessment. So I have my structure. It is vulnerable to wind. Please provide me the probability of failure of being in a damage state for a specific wind speed. The second leg is the hazard. So, for instance, how possible is to have 49 meters per second at this area? And this was provided by the climatological model. That's why the risk was based on the fragility assessment and the climatological models, the hazard assessment. And based on that, in the back end of the platform, you can estimate the risk. Usually, in performance-based engineering and relevant literature, the risk is expressed as the annual probability of failure or the mean annual frequency. Typically, for low values of annual probability of failure, assuming a Poisson assumption, the mean corresponds to the mean annual frequency. That's why here we present the mean annual frequency, which means how many times in an average year I'm going to be in that state. As you can see, we end up with very low mean annual frequency, which if you take the reciprocal, you end up with a return period. For instance, an annual frequency of 0.1, so 0.001, it corresponds to a return period of 1,000 years. As you can see, for the Katinara Hospital, and given even in the year of 2050, since no corrosion effects are expected, we end up with very low mean annual frequencies, or even for the moderate states. And of course, the moderate state has the highest annual frequency, and then the severe, and then the collapse. And based on this result, we can end up with a corresponding social impact graph, where the user can say that, okay, this is I can say the vulnerability, the risk of my structure. Let's see how is correlated to the social. Am I going to have social impacts? So should I be prepared for that? And this is more or less the integration of the pilot 3 study in our platform, the RISKADAPT platform. So I think questions. So I don't know if you have any questions, and then I can move to pilot. Oh, yeah, sorry. Okay. So also, and thanks for remind that, we have the social. We have a couple of extra modules which provide the social parameters, and what is that is the social, the data, the input data that were used in the social impact assessments can be displayed on a map of the region of the entire region of Trieste. Here you can display, the relevant parameters. There are various parameters related to social and demographics, and also if you would like to see to have a focus on the asset, you can also see the exact area of the asset. And we have another module, which is the climatological module. This is based on NetCDF data that were provided by FMI. And here we have integrated the monthly maximum temperature over the period 1979 to 2019 under the worst case scenario of SSP, which is the SSP 585. And the user can select a year of interest, and then by pressing the button, an animation starts and can provide the monthly maximum, how they were evolved from that year up to 2019. So these are more related to the climatologist, more interested. I think that these are the main functionalities, and we covered pilot 3. I think we saw all of the work that has been Vasilis.
Yes, I would say should be better if should be better and substitute the word collapse with the word critical.
Okay.
This is important because may be a difference. And then I'm not sure this would be helpful the structural engineers if you have to say that no damage, let's say moderate damage is when the safety factor is between 1.3 and 1.5, and critical should be between 1.1 and 1.3. Less than 1.1, we don't take into consideration, means we have to do further,
Okay.
further studies and so on, because we are quite at one is between life and death.
Yes, this is a very good comment, and of course we don't have time to talk more about the performance-based assessment, which is based on the different damage states. Exactly. Of course. But the damage states are usually, specified by the engineer or by the coach. There are some limits, and when you exceed these limits, you can say that I'm in a moderate or in severe, etc. And Vasilis provide us with those limits, and after based on the structural analysis that were performed by Technique and the probabilistic analysis on those performed by RISA, we determine the different damage states. But of course, in another case, for instance, in the case of the bridge, the maximum drift ratio, I think, was considered as a damage state, the percentage of drift ratio, etc. So I think that we can show now the pilot for
what will be implemented in the summer is the total risk and MIS.
Yes, of course, this is not the final version of our platform. We will integrate the total risk assessment that has been performed by our partner RINA, and also the model information system. You have also the home pages. It's the logic, the flow is the same. But and the asset initialization for the administrator. And let's go to the risk assessment. We move to an exotic Eastern Asia, Hong Kong. And for Hong Kong, we had 3 different assets. They were provided to us 3 different tall buildings, skyscrapers. I will pick the Hang Seng Bank. And as Professor Lee from the University of Hong Kong discussed previously, these assets are vulnerable to glass window breakage due to typhoons, so high wind speeds. And the platform works in a similar way as Pilot 3. If I chose the Hang Seng Bank Central, the map zooms on the location of the asset. I click and I get the window with the general information of the asset. And in this case, I have the structural model characteristics. Our material of interest is glass, of course. The structure has also steel and concrete, but for the case of the RISKADAPT, we are mainly concentrated on the glass behavior. And for adaptation, we made the assumption that the glass thickness, the original glass thickness, is of 6 millimeters. So for different adaptation options, we consider the increase in the thickness of glass. So we experiment with various values of potential glass thicknesses from 8, 10, 12, etc., up to 20 millimeters. And again, since we know the factor, the wind speed, the fragility assessment approach is the co-specific. If you are interested, you can download the BIM model. And for the scenario builder, here we have two different groups of scenario. The ASI scenario, which is how is the asset since its construction up to the year of interest. For glass, we didn't have any material degradation models, so we did not consider the material degradation due to climate. But the user can estimate the risk of glass breakage based on the CP, which is the pressure coefficient, and based on the calculations provided by the University of Hong Kong. We have two options. We have the pressure coefficients estimated by computational fluid dynamic analysis or by the code. If I go with CFD, I'm interested in the CFD. Then for here we have data only for 2050 and 2080. We provide with the data. I will press the year, and then the climatological model will have only one, the RCP 8.5, which is relevant to SSP 5 8.5. And if I select the climatological model, I get the corresponding fragility curve. Professor Lee showed the equations behind these estimations, and what I get is the probability of have a glass breakage, a glass failure for varied wind speeds. Consider that in this case the glass has a thickness of 6 millimeters. And then based on the data of the year of interest and the corresponding distribution of the wind speeds. So how possible is it to have a wind speed of a specific magnitude? I can get the estimated probability of failure, which is 6.6 times 10 minus 3. If now I'm interested in following the code and not the CFD, you will see that the fragility curve is the same, doesn't change, but the probability of failure changes, and I think that it is lower. So probably the CFD overestimates the risk, or there is something, and there is a different result. If I would like to go to 2080 with the code, again, the fragility curve remains the same because it depends on the specifications of the glass, but you will see a different probability of failure, and it is larger. See, based on the climatic models, for that area, Hong Kong, the wind speeds are going to increase based on the worst case climatic scenario. And now let's go to the what if. The what if is, if, okay, I have my glass, I know its properties, its thickness, etc. Let's see if I want to make it safer. If I want, what means safer? To reduce the probability of failure. And I can play with the different options. Let's consider of using a glass thickness of 16 millimeter. Again, I can go with CFD or code. Let's pick the code. The year of interest, 2050. Climatological model is one. You have a different fragility curve, and that fragility curve has moved to the right, meaning that for the same wind speed, the 60 millimeters have lower probability of failure, which is plausible. It's logical because the thickness is larger. So, and I can estimate, the platform estimates the corresponding risk, which is really lower. It's 10 minus 20. And if I want to see in year 2080, the same fragility curve, but I have a larger probability of failure. And if I use a 20 millimeters, then the models provides a negligible probability of failure. So based on the data we have and the methodology provided by code, the HTM standards, we result with negligible probability. And if you want to go to another asset, you can close this window, go back to the full map, and pick another asset. It's the immigration tower, and then you have the corresponding information, the structural model characteristics, and the same scenario builder, and you can, see the behavior of the other asset. And this is how the platform was applied in pilot 4 and for the Hong Kong towers. Of course, in that case, in pilot 4, we did not consider any social parameters because on the grant agreement, the plan was the social parameters to be estimated and studied only for the European pilots. I think that we have covered.
Yes, I think we have covered the both pilots we would like to present. There are another 2 pilots. The important thing here is further to all the structural analysis presented by Dimitris, and thank you, Dimitris, for this, for your time. And all the information integrated in the platform, we can see that the 2 different assets have been treated from the engineers, have been analyzed in a different way, and the platform could find this, has been developed in a way so that in any case an asset is initialized, it can be integrated in the platform through the asset initialization, and this makes it this is an innovation from further to all the results and innovation from our side.
So I would like to add that the reason of developing this platform is since the climate change adaptation and the risk of infrastructure, of critical infrastructure, they relate a lot of, they combine a lot of different aspects. It's an interdisciplinary process. We have social scientists, we have civil engineers, which is the core of the project, we have IT, climatologists. All these information are interrelated, but usually they are scarce. They are, how can I say that, in different sources available. So it's an idea to provide all this information in a platform, so every stakeholder, even it is an engineer, even it is a climatologist, even it is the municipality which designs the policy and would like to know the assets, the stock, can be benefited from having a tool like this. And these are the first, it's the first step. We picked 4 pilots, 4 different structures, a bridge, a building, steel towers and skyscrapers, but this can be expanded. This can be expanded to more buildings, to clusters of buildings. Let's say I have a steel tower of some type, and I would like to have it to see what is the behavior in different areas. For instance, the transmission towers. A whole country can have thousands of transmission towers. And if you are not only the company, the owner of the grid, but also an insurance company, and you are asked to insurance to this structure, you need to know how risky is. Am I going to have high risk of failure? So then I will ask for more money. It's like the health insurance. If you go to a private company, they have you have blood tests, screening in order to know if you have a good quality of health or if you are vulnerable to specific health issues. So a lot of different stakeholders can be benefited. And I think that at the end, this is one of the outcomes of this project, that we brought together people from different disciplines. We were universities, companies, but also public authorities. We did a collaborated effort